Forensic science bridges the gap between science and justice, utilizing scientific methods to analyze evidence. Techniques like DNA profiling, fingerprint analysis, and toxicology are pivotal in solving crimes. These methods ensure accuracy and reliability, transforming raw data into compelling evidence that can uphold justice in courtrooms. Forensic science has evolved significantly since its inception. The scientific revolution played a pivotal role in transforming criminal investigations, introducing methods like fingerprint analysis and DNA, deoxyribonucleic acid, profiling. These advancements have enhanced accuracy and reliability in solving crimes, bridging the gap between ancient practices and modern techniques. The term forensic originates from the Latin forensis, referring to the Roman forums where legal debates occurred. In these public spaces, evidence and arguments were presented to influence public opinion. This practice of evidence-based reasoning established the groundwork for today's scientific investigation techniques. St. Thomas the Doubter embodies the essence of forensic science through the Doubting Thomas principle. This principle emphasizes the necessity of evidence and skepticism in investigations, urging forensic scientists to challenge assumptions and seek proof. It underscores the critical role of questioning and verification in the pursuit of justice. Mathieu Orfila pioneered toxicology, revolutionizing poison detection in human tissue. Alphonse Bertillon introduced anthropometry, the first systematic body measurement identification. Francis Galton classified fingerprints for reliable identification. Leon Lattes developed blood typing from dried stains. Albert Osborne legitimized document examination in court. Edmond Locard established the crime lab, formulating the Locard's exchange principle. Sir Arthur Conan Doyle's Sherlock Holmes revolutionized crime detection in literature, bridging science and fiction. Holmes's logical methods and focus on physical evidence inspired real forensic techniques. His use of observation, deduction, and scientific analysis showcased how these methods could unravel complex crimes, influencing the development of modern forensic practices. Locard's exchange principle is pivotal in forensics, encapsulated by every contact leaves a trace. This principle asserts that whenever two objects interact, they exchange material. This exchange forms the foundation of physical evidence, crucial for crime scene analysis and solving cases through meticulous examination of traces left behind. Crime scene investigation requires a systematic approach to preserve and analyze evidence. First, assess the situation to ensure safety and identify victims. Detain and interview witnesses and suspects to gather initial information. Protect the scene by establishing perimeters to prevent contamination. Document everything meticulously, including observations, times, and initial findings, to maintain the integrity of the investigation. First responders assess the situation by ensuring safety, identifying victims, and determining the scene's scope. They detain and interview witnesses and suspects to gather initial information. Protecting the scene involves establishing perimeters to prevent evidence contamination. Detailed documentation of observations, times, and initial findings is crucial for a thorough investigation. The primary crime scene is the original location of the crime, holding crucial evidence. Secondary crime scenes are related areas with additional evidence. Key players include the suspect, believed to have committed the crime, and any accomplices who assisted. An alibi is evidence proving a person was elsewhere during the crime. Crime scene protocol involves 4 critical steps. First, interview witnesses and first responders to gather initial information. Next, examine the scene to identify evidence and analyze entry and exit points. Document the scene with photographs and sketches, ensuring precise measurements. Finally, process the scene by collecting and preserving physical evidence and testimonial statements. Photographs must capture the scene unaltered, using wide-angle shots for context and close-ups with scales for detail. Multiple angles of key evidence are essential. Rough sketches are made on site, later refined with precise measurements. These sketches map evidence relationships and use a coordinate system for accuracy, ensuring a comprehensive visual record. Forensic evidence is categorized into several types, each playing a crucial role in investigations. Biological evidence, such as fingerprints and DNA, uniquely links individuals to crime scenes. Trace materials, including fibers and glass fragments, indicate contact and transfer. Ballistics evidence reveals weapon types and firing patterns, while impression evidence, like tool marks and shoe prints, provides unique object patterns. Physical evidence serves as a silent witness in investigations. Biological evidence, like fingerprints and DNA, uniquely links individuals to crime scenes. Trace materials such as fibers and glass fragments indicate contact and transfer. Ballistics evidence reveals weapon types, while impression evidence like shoe prints shows unique patterns. Documentary evidence uncovers identity and authenticity. Trace evidence, though microscopic, plays a pivotal role in investigations. Skin cells, hair strands, and fabric fibers, invisible to the naked eye, can link suspects, victims, and crime scenes. Advanced microscopy and chemical analysis unravel the narratives hidden within these tiny fragments, providing crucial connections in forensic analysis. Testimonial evidence includes statements from witnesses, victims, and suspects, but is prone to memory bias, stress, and deception. In contrast, physical evidence, such as tangible items from crime scenes, is objective, reliable, and hard to falsify, making it preferred in court for its scientific reliability. Specialized forensic disciplines enhance criminal investigations. DNA analysis identifies individuals via unique genetic material. Toxicology detects poisons and drugs in body fluids. Ballistics examines firearms and trajectories to reconstruct shootings. Forensic pathology determines cause of death through autopsies. Digital forensics recovers data from electronic devices, crucial in modern investigations. The arsenic trial of 1840 highlighted the pivotal role of forensic toxicology. Marie Lafarge was accused of poisoning her husband with arsenic. Initial tests were inconclusive, but Mathieu Orfila's advanced chemical analysis confirmed arsenic in the victim's body. This case established forensic toxicology as a legitimate scientific discipline, setting a precedent for chemical evidence in courtrooms worldwide. In the 1840 Lafarge murder case, Marie Lafarge was accused of poisoning her husband with arsenic. Initial tests were inconclusive, but Mathieu Orfila's advanced chemical analysis confirmed arsenic in the victim's body. This pivotal case established forensic toxicology as a credible scientific discipline, setting a global precedent for chemical evidence in courtrooms. In 1882, Alphonse Bertillon revolutionized identification with anthropometric measurements. His system included 11 precise body measurements, photographs, and physical descriptions. This method significantly reduced mistaken identity cases and laid the groundwork for fingerprinting, marking a pivotal moment in forensic science. In 1892, Francis Galton's groundbreaking study established the mathematical basis for fingerprint uniqueness, proving they remain unchanged throughout life. His work laid the foundation for a systematic classification system, which is still integral to modern forensic science, ensuring accurate identification and enhancing criminal investigations. In 1915, Leone Lattes revolutionized forensic science by developing a method to determine blood type from dried stains, even months old. This innovation allowed investigators to link suspects to crime scenes, exclude innocent individuals, and reconstruct crime scenarios through blood spatter patterns, significantly advancing criminal investigations. In 1932, the Federal Bureau of Investigation Crime Laboratory was established, marking the first national forensic facility. Handling over 50,000 cases annually, it operates 13 specialized units. This lab pioneered forensic standardization, evidence protocols, and comprehensive training programs, setting a global benchmark for forensic laboratories. Modern forensic techniques leverage advanced technologies to revolutionize criminal investigations. Digital forensics, chemical analysis, and biometric systems enhance evidence accuracy and reliability. Innovations like 3D crime scene reconstruction and artificial intelligence-driven data analysis provide unprecedented insights, ensuring precise and efficient case resolutions. DNA profiling begins with collecting samples from sources like blood or saliva. In the lab, specific DNA regions are amplified and analyzed to create unique profiles. These profiles are compared against databases such as CODIS for matches. With a 99.9% accuracy rate, DNA evidence has exonerated over 375 death row inmates since 1989. Digital forensics is pivotal in modern investigations. Mobile device analysis retrieves deleted texts, call logs, and location data. Computer forensics uncovers hidden files and internet history. Network investigation traces digital footprints and analyzes traffic patterns. These techniques are crucial for solving cybercrime, fraud, terrorism, and crimes with digital elements. Forensic laboratories utilize advanced instrumentation like scanning electron microscopes for trace analysis, gas chromatography for substance identification, and mass spectrometry for molecular analysis. Integrated databases such as the Combined DNA Index System, Automated Fingerprint Identification System, National Integrated Ballistic Information Network, and Integrated Ballistics Identification System enhance DNA, fingerprint, ballistics, and material analysis. Multidisciplinary teams leverage chemistry, biology, physics, and computer science for precise evidence analysis. Ensuring evidence integrity requires meticulous contamination prevention and strict chain of custody protocols. Balancing investigative needs with privacy rights is crucial, particularly in digital forensics and DNA collection. Upholding scientific rigor involves avoiding confirmation bias and ensuring peer review. Quality assurance demands rigorous testing, proficiency standards, and continuous training for forensic professionals to maintain objective analysis standards. The future of forensic science is being shaped by artificial intelligence and machine learning, enhancing pattern recognition in fingerprints and facial analysis. Portable technology enables rapid DNA analysis and chemical identification in the field. Advanced genomics, including phenotyping and proteomics, expands identification capabilities. Virtual reality aids in crime scene reconstruction, while global integration fosters international database sharing and standardized protocols. Emerging trends in forensic science are revolutionizing investigations. Artificial intelligence and machine learning enhance pattern recognition for fingerprints and facial analysis. Portable technology enables rapid DNA and chemical testing. Advanced genomics expands identification through phenotyping and proteomics. Virtual reality crime scenes aid jury presentations and training. Global integration fosters international database sharing and standardized protocols for cross-border investigations. Forensic science unites meticulous scientific methods with the legal system's quest for truth. Every trace, from fibers to digital footprints, is crucial in solving crimes and safeguarding the innocent. Emerging technologies promise enhanced certainty and fairness in justice. Thank you for delving into this captivating field.